Hello, everybody. Good to have you here. Feel free to say hi in the chat. And if it's your first time, as always, let us know where you're coming from. Anybody have any fun summer plans lined up? Also, let us know that. We finally have had some good weather in Pittsburgh, so just let us know if you've got any interesting projects or travel. I know I've got some summer plans. And part of that, and speaking of projects, is our next round of programming projects starts next week. And I also have a new course that we're going to run as a mini course to kind of bridge us over to when we start Great Ideas in Computational Biology. And we're going to start that in about 6 weeks. So our new course is going to look at how to use AI effectively to not just vibe code a project, but understand how to do all of the research that might be involved in figuring out how to educate yourself around something that you want to work on, how to discover something that you're interested in doing, and then how to effectively execute this in a way that ensures that you're doing so correctly and in a way that makes sure that you're not just watching the machine do something amazing. So we're going to start that in mid-June. Both of these initiatives, both our new AI course as well as our programming projects next cohort starting next week, they're both going to be for our Philomath members. So there's information always on that in the description of the video. And if you sign up to be a member, you can sign up for a project starting next week. And that'll also unlock the ability to take my short course. It's going to be about 4 weeks worth of material showing you how to use AI effectively to learn, as well as to, create something that can be like a component of a portfolio. So that's going to be an exciting summer. I hope everybody's doing good. Assembly languages for masochists. That's probably a good transition to what we're going to do today, which is something a little bit different. I hope that I will leave you with the impression that if you've seen assembly language before, that it's actually not so bad. Normally how that works, I'll just say how it works is when I've taught this topic, and I can't believe I've taught this topic for a long time. And when I first started teaching programming, it was an inherited course, and I've changed everything about the course over the years, except for this one particular topic. And it's because there's a natural progression that all of my students have always had with this, which is that they come to this topic for the first time and they feel like it's very challenging. Maybe it's the most challenging thing in the entire course. And then they always, after they've had a chance to learn about it and complete some exercises on it, they will always report that it's the most meaningful and helpful topic throughout everything that they've done. And so it's interesting because most people do not program these days in assembly language. That's not something that people would see a lot of utility in. And we might hit a point soon where people maybe no longer see the utility in learning something like Python. So maybe this is too close to the bowels of the computer for somebody to need to know in order to work with this effectively, work with the computer effectively. And I would say assembly language is a good example of how something that most people don't need can actually still very much grow your brain and your ability to solve problems and more importantly, appreciate how it is that the computer is actually working. So we're going to do something a little bit different, not just in terms of the topic that we're going to consider here. And we're going to start on a journey that I like to frame as the journey to the dark heart of computer science, because we're delving deeper into what the computer is actually doing. And when we do that, even though we're in the midst of a revolution where computers seem amazing, and they are, we're also going to gain a little bit of perspective over what are the types of problems that computers can solve, what are the problems that computers find difficult, and what are the problems that computers actually cannot solve. So there's a lot to say about all that. We're also going to have a little bit of a different formulation here in this setup here, with going through a lot of this material just on the level of some slides that I have. There will be an opportunity to see a demo, but it's going to be important for me to try and give you as much context as I possibly can before we actually take a look at anything on the level of code. If we just start opening up the application that we're going to work with and start coding, it's going to be very challenging to teach exactly what in the world is even going on. That sounds intimidating. It's not, because today we're going to ultimately get to a program in assembly language. That program is going to do something very simple, and I'll kind of leave it for a surprise as to what we're eventually going to be able to do, but I will at least say that I think the course is going to come very much full circle for a lot of you. So if you've joined us from the beginning of the course, I like having the opportunity of having a point where, I mean, obviously we have done an enormous amount in this course, right? Where we've started with, what are variables before we even talk about functions and setting x equal to 3 and things like this. We've built up the entire course up to the point of being able to do advanced object-oriented programming and then transition towards parallel programming with hundreds of lines of code in our projects that we've been building. We're going to try and take that back to the start of the course, and I'll show you what I mean with that the next time we're together. We'll show a demo tonight when we do get to the level of code in an application called Visual X Toy. And I've always looked at maybe trying to change the application that we use, and there are more complex, advanced ways in which I could show you this stuff. I still, at the end of the day, really like Visual X Toy because the purpose is not to try and make you somebody who's going to be a systems level programmer today. The purpose is to give you the appreciation for what's actually going on inside of the computer. And I just feel like this is a nice, simple application that kind of, even though it is a classic application, it has stood the test of time in terms of showing you how everything is working. If you're interested in following along, there's a link in the description with a download. So you can get the Visual X Toy application. That's not that important for this time because, as I said, the program that we're going to look at is a little bit rudimentary given everything that we've done up to this point in time. And yet, just as we were able to ramp up previously, we're going to be able to ramp up with the way that we're thinking about programming in this particular time. So if we think about programming as clearly and correctly telling a computer what to do, that could be on a very high level. These days that can be with AI. So that's another plug for my AI course, because that, good effective prompting also in a very serious sense is programming. We're going to be going in the other direction first tonight, which is, eventually at the end of the day, every computer is an electrical machine. And so how is it that something like a for loop or something like, the programs that we've encountered in this course, how is it that they get represented as electrical signals? And we're going to have, the ability to delve into the computer and understand that. I will also say what we're going to do today is hopefully a little bit lighter than last time. We were on the stream for like 3 hours the last time we had a chance to be together. So I'm not planning on this taking quite that long, although there are going to be opportunities for us to interact in the chat, opportunities for me to give you little exercises or ask you, what you think about something. So I'm going to go steadily. My goal is not to rush through it, and it's also not to cover an enormous amount of material tonight. This might be an opportunity, though, to, if you've got a pencil and paper handy, to take some notes on what we're doing. I think that'll give you some context, and you can always come back to this, of course, but we're going to start our journey. So without any further ado, we'll head towards the dark heart. And as always, please like and subscribe. It helps us stay visible. And if you'd like some deeper engagement, join our mailing list, join our Discord. as we continue to roll out new courses and new exciting ventures. That's it for me, though, for now. We're ready to get started, and let's code. Although it's going to take us a little bit of time to come back to the coding. And if you have any questions, as always, let us know. All right. So we're going to talk about assembly language and how the computer is ultimately organized as this electrical machine. And to that point, what we see here is something that's very important for making your programs run more effectively. But these are memory cards. So the more of these that, more memory that you have, if your memory is RAM, the more applications you're able to run. That's very useful if you're working on a machine with multiple cores, for example, because if you have several cores available, you also need memory available to your programs so that they can store data as the programs run. So not only do we need multiple cores, but we also need a bank of a lot of memory. Those two things are going to go hand in hand. That's going to allow you, for example, if you're running an email app, you need to store messages that are coming in, contacts perhaps, and these sorts of things. If you also have a game that's running, you need to store, different dragons and wizards or whatever in the game and their attributes and these sorts of things. And so every application needs to be storing some data as it's running. And that's where memory is going to be really important. We also, I also want to point out that a computer is really just an electrical machine. And when you zoom far enough into a chip or a central processing unit, for example, or you zoom far enough into the RAM, what you see is many millions, billions of transistors, which are, the classic sense is to think about these as little electrical switches. Thinking of them as on or off, I think, is helpful, but really I think it's more of a high and low state. So there's an amplifier where each transistor has an amplified state, and the CPU or your computer, a chip, is going to always consist of a lot of these transistors. They get linked together onto this chip. And the old school way of referring to a chip is an integrated circuit. But today's question is, if I understand that even on a high level, how is it that I take code like this Python function and then convert it into instructions that are represented on the level of electrical instructions, which means that on the level of transistors, all of your transistors have a high or a low state. And this is where, if you to use kind of an age-old trope, everything in a computer is ultimately represented in binary. You think of everything as ones and zeros. You probably have seen that, but you might not have a great appreciation for what that really means and how that idea of everything in a computer is ones and zeros, how does that have anything to do with Python code? So in this particular case, we've got a mystery Python function. We can see it takes two integers. It doesn't return anything. It eventually prints something. And we're curious to know how something like this, a relatively straightforward function from the foundations of the course, all it has is a while loop in it. It sets some variables. It does a little bit of arithmetic with them, and then it prints R6. How is it that eventually corresponds into ones and zeros? I think that's probably not ultimately very clear. As an aside, I might ask you, if you have any sense on what this function does, let me know. Anybody have any ideas? Or maybe we'll just save. We won't spoil the surprise. I've asked this for a few years now. No one really ever has any ideas. It's clear that it does something. It sets a couple variables, has this while loop, it does a few things, and then it finally prints our sings. Kepi, you have an idea? I like that. Let's see if you're right. Okay, but we'll have to hold on to that because this is going to correspond to what you're saying, and it will eventually be a function that we can understand on the level of ones and zeros. And you might say, well, this is written in a very bizarre way. Correct. And we're going to hang on to that for now. But we want to know, how is it that something like this becomes ones and zeros? A long time ago, we looked at a problem of finding the most frequent substrings of length k, which we called kmers, in a string text. So we had an integer k and a string text, and we wanted to return the most frequent kmers in the text, meaning we count up the number of occurrences of every kmer substring of text, and then we take the ones that are the most frequent, meaning the ones achieving the maximum number of counts. And sometimes we had a tie. This is not a hard problem, I hope, if you've made it to this point of the course, because we know, well, we could slide a window over the text, create a dictionary, and keep track of how often each kmer occurs. And then at the end of that, just look for the max value of the dictionary. And then we ask ourselves, what are the substrings that achieve that maximum? So we can split this into multiple steps. And one of the things that I want to make clear is that there are a lot of programming languages. They all have different strengths and weaknesses. In the case of Python, it's mostly weaknesses. But we can look at how code for this might work in different languages. Here is a language called C0, and this is a solution to the frequent words problem in C0. So this is a version of C that has a little bit of extra functionality associated with it. And this is a language that I would say they don't teach the language. It's sort of assumed that everybody can kind of pull themselves up by their bootstraps a bit. But this is a course that's taught to first-year undergraduates in the School of Computer Science at CMU, where they're expected to be able to be comfortable in programming in this language. It has a lot of, C in general has a lot of strengths to it. It's a very fast language, but you might look at this and think, I don't know if I would be the most comfortable taking a course in this language. And if you think that, I think there's good reason for that, and I'm going to explain why that's the case, even though this language has a lot of strengths. Let's look at another implementation of frequent words in a language called Go. So Go has great support for parallel and distributed programming, but here's its implementation of finding the frequent words of a string, where we're also taking this parameter k to indicate the length of the substrings that we're looking for. And in this particular case, it's like being at the eye doctor. If I offered you 1 or 2, you probably don't even need to have ever programmed before to pick number 2. There's something about it that just looks a little bit more natural. And then if we flip the eyeglasses again, the lenses again, and say 1 or 2, where number 2 is Python, and here is the Python implementation of finding the most frequent words of length k in a given string, I would imagine that you would probably pick number 2. And this is what this is getting at is, I think, this is why so many programming courses don't try to teach beginners at this level. I would say very few programming courses designed for beginners would try to teach them in C. There are some courses in introductory programming in a language like Go. I really like this. In fact, I taught programming to a lot of beginners using Go as our model language for a long time. But a lot of people really have wanted to come to programming from the perspective of a language like Python, because when you look at this automatically, again, even if you've never coded a line in your life, this probably just looks a little bit more comfortable. Now, the text even got bigger between 1 and 2, and that's because this implementation uses fewer lines, but it also looks quite a bit closer, I would say, to human language than the other two languages. So C0 looks very alien, whereas Python might look very familiar. And frankly, that's not the best reason to pick a language. But from the perspective of people coming to programming for the first time, it's a big reason why people have chosen Python so much. The downside, as we have seen, of Python is that sometimes it can be, even though it has this similarity to human language, it also can be somewhat slow. And programming languages in general are going to fall on a spectrum. At the far left of this, we have what we would call low-level programming languages, which means that they're, in a sense, and we're going to delve into what we mean here, closer to the machine. And that's going to give you a lot more control over, being able to change things in the machine. Whereas the farther to the right that you go on the spectrum, you're going to get higher level languages that are closer to human language, or appear to be closer to human language, that come with a lot of bells and whistles and features. Python's a great example of a language like that. Often it gives you 6 different ways of doing the same thing. And a language like C might give you 0 ways of doing that. It might say, we just assume that you're going to implement this idea on your own. But the downside of that is that if you have a lot of one-size-fits-all solutions implemented within the language for you already, then it can mean that things slow down. So in the middle of these, you have mid-level languages. Go falls in the middle around where Java is. And so you have a little more machine control than something like Python, but it's going to be a little bit more comfortable to work with. If you were manually coding anything, then it would be the case that if you were working in something like C. I've been mentioning this as this kind of beating around the bush here in terms of what we mean precisely by CPU and what we mean by RAM. And there's a classic conceptual architecture here that we could examine, which is to think about the RAM as this very large storage facility of sorts, where each bay of the storage facility has some finite amount of storage associated with it. And the more of that we have, the more memory our programs or applications are going to have access to, so the more they can do. But at the end of the day, this RAM is going to store our data as strings of binary numbers. Each word or each address of the RAM is going to correspond to, think of it as a bunch of transistors that all have a 1 or a 0 state. So they're either high or low, on or off, 1 or 0. We represent these with these binary digits 1 and 0. But the central processing unit is going to contain a smaller collection of these addresses that are internal to the computer. And the analogy or the picture I want to draw for you is that you have a huge bank of RAM. So you may have billions of addresses of RAM, but you have a small number of registers. Maybe your computer has 16 or 32 or 64 registers, something like this. And those registers are used for fast operations. So the central processing unit is pulling in data from the RAM. It might make a very fast computation by storing some of those data in registers, and then it writes back to the RAM. And the reason why it's organized in that way is because for complicated electrical engineering reasons, this is what produces the most efficient computer, is to say we have a huge storage facility, but at any given point in time, I can store a small number of things internally. And if I run out of space, I just need to push it back to the RAM. And there's a little more to it, of course, because if I say read from some particular addresses or write to some particular addresses, they may be reserved for something like the computer display or to perform some task or writing to the hard drive. So there are particular addresses that might cause additional behaviors, but I think that there's a natural way of thinking about a lot of tasks that the computer does as it's got access to a small amount of data internally that has this large bank of additional resources for storing data represented by the RAM. In both places, in the registers and in the RAM, we're going to be representing what is stored in that location as a string of ones and zeros. And that means that our arithmetic at the end of the day, if I want to add two numbers, for example, well, those numbers are represented as these strings of ones and zeros, which means that we need to have an appreciation for and a comfort with doing arithmetic in binary or in base 2. So I'd say this is one of the areas in which classically mathematics is so necessary, and a strong foundation in mathematics is so necessary for a complete understanding of many topics in computer science, and this is absolutely one of them, that you may have become very comfortable thinking of a certain number as 4,256, and there is an abstraction of what that number represents that is, in a sense, more general than this concept that we apply to it of 4,256. I think if you go deep enough into mathematics, eventually what happens is, as some mathematicians have sadly come to realize, is that the numbers start to take on different characters and personas. And so you might think of 17 as having one persona and 4 as having a very different persona. That's not a depth of mathematical study that I think is necessarily a good thing. But in this particular case, I want you to think of the number as a higher level concept. But how we represent this particular number is to say it's as if we have 4,000 of something, 200 of something, 50 of this unit, and 6 of the unit. And if we combine all of those 4 quantities, then that adds up to the particular number that we're interested in. But we don't have to, of course, represent the number by splitting it out in terms of those 4 individual quantities, 4,200, 5 tens, and then 6 ones. We could represent it by a collection of other quantities. And if we are only allowing ourselves 2 digits for representing the number, then another way that we could represent this same number that we think of as 4,256 is 1 times 2 to the 12th. And 2 to the 12th is 4,096, because 2 to the 10th is 1,024. So 2 to the 12th, this particular number here, we think of that as 4,096. And you notice that's not quite 4,256. So we also would need to have one factor of 2 to the 7th. And 2 to the 7th is 128. So we would have 4,096 plus 128. And then we also need 32. 32 is 2 to the 5th. So it turns out that 32, 128, and 4,096, when you add those 3 numbers together, you get 4,256. And that puts us comfortably back in our base 10 representation of the number. But in terms of base 2, where the only allowable digits are zeros and ones, we wind up representing the same number as 10000, 101, and then 5 more zeros. So this would be the ones place, and this digit would represent not the tens place, but the twos place. The next would be 2 squared, or 4. This would be 8, 16, so this is our 32. This is 64, 128, and so on up to 4,096. The point being, we can represent the number in base 10. We can represent that same number in base 2. And for any number that you might pick, we're always going to be able to find some base 2 representation of it. And that representation is going to be unique. Writing everything in binary within the computer, though, would be tedious. So even though, yes, the computer is represented as sequences of ones and zeros if we're storing data, we're often going to use base 16, or what is called hexadecimal. And I'm going to explain why that's going to be such a natural thing to do here soon. But I'm going to show you the base 16 representation of the number that we saw before as 4,256. Because we have base 16, that means we have 16 different digits. In base 10, we have 10 digits, 0 through 9. In hexadecimal, we have 16 different digits, which means that we get 0 through 9, but we're also going to have A to represent 10, B to represent 11, C to represent 12, D to represent 13, E to represent 14, and F to represent the number that we think of as 15. So we're going to have even more digits than we normally have. We're going to have 16 total, 0 to F. So this number that we think of as 4,256 in terms of base 10, when we look at it in terms of base 16, now each position has a different meaning. So the rightmost digit still represents the ones, but this second to the rightmost digit is going to represent the 16s column. This is going to be 16 squared, or 256, and this is 16 cubed, or 4,096. So the number that was 4 times 10 cubed, plus 2 times 10 squared, plus 5 times 10 to the first, plus 6 times 10 to the 0, is 1 times 16 squared, 16 cubed, no factors of 16 squared, and then A, which is what we would call 10, but A factors of 16 to the 1, and then no ones. So here we see that this number is 1 times 4,096 plus 10, or A, times 16. You add those two things together, you get 4,256. But in base 16, the representation of this number is just then 1, 0, A, or 10, and then 0. So you can pick any base that you like, and you can represent any number you like in that particular base. And I'll say this is a great opportunity for me to ask you a question so that we can just kind of test our understanding, which is, say I've got the number A7D in base 16, and remember that the D corresponds to the ones column, the 7 corresponds to the 16s column, and the A corresponds to the 16 squared, or 256 column. Remember that A is 10, B is 11, C is 12, and D is 13. So take a moment and try converting that number in hexadecimal both to base 10, what we're comfortable with, and then also do a conversion of it to binary. So I'll give you a chance to do that. And as you do it, I want you to think about which of these two directions is easier for you to make the conversion of A7D in hexadecimal. If you have any questions, let me know, but I'll give you a couple minutes to think about it. I also started a poll. So you can tell me what you think. Which of these conversions is easier? Converting A7D in hex to base 10 or converting it to binary? All right, Meg's telling us 2685 as the base 10 representation of this number. And I'll believe that. So A is 10. So this is 10 times 256, which is 2560. Then we have 7 times 16, which is 112. And then we have 13 times 1. And when you add those three things together, you get 2560 plus 112 plus 13, which winds up adding together to give you 2,685 in base 10. And then as for binary, the question becomes, what should we do? And if you found the binary representation of this number, probably what you did is you started with the base 10 representation, and then you converted it to binary by saying, well, what's the largest power of 2 that's smaller than 2,685? So in that particular case, you might say, well, it's 2,048. You'd go from there, subtract that from 2685, a very natural thing to do. And as a result, everybody looks at this, and the same is true, I think, for the chat. Everybody looks at this and says, it's far easier to convert A7D in hex to binary, or to base 10, than it is to binary. And that's great, because that is incorrect. It's actually way easier to convert a hex number to binary than it is to base 10. And that's because it's much simpler than it at first glance might seem. And I'll show you why. So, trying to advance the slides. All right. So if we look at our base 16 representation of this number A7D, we know that that is 10 times 16 squared, or A, plus 7 times 16 to the 1, plus 13 times 16 to the 0. And if we were to represent that, in base 10, we'd say it's 2560 plus 112 plus 13. We get 2,685. Let's go back to how we represented that, though, and say, well, it's 10 times 16 squared plus 7 times 16 to the 1 plus 13 times 16 to the 0, and it also is 10 times 2 to the 8th. So 16 squared is 2 to the power of something. You might say, well, how do I know that? Well, because every one of these numbers has 16 as the base. 16 is just 2 to the 4th. And so 16 squared is 2 to the 8th. 16 to the 1 is 2 to the 4th. 16 to the 0 is the same as 2 to the 0. But now I've represented this as a bunch of products of powers of 2. And all those powers of 2 are divisible by 4. So you will note that the leftmost number, 10, in base 2, that's 1010. Okay? You might say, well, how do I know that? Well, this is the 1s, 2s, 4s, and 8s. So when you see this number in base 2, this means 8 plus 2. 7 is 4 plus 2 plus 1. 13 is 8 plus 4 plus 1. And so the representation of the green, blue, and orange numbers in base 2 are shown as these strings. So everything here is really, I've represented this number, maybe in base 10, but everything here is essentially kind of happening in base 2. The question becomes how to combine all of this stuff together. And the critical insight is, if you multiply a number in base 10 times 10 to the 8th, you're going to access something in your brain, a very deep-seated memory where somehow at some point in time you had a math teacher who impressed upon you that when you multiply a number by 10 to the 8th, we know what happens, and you sort of, as if you've been brainwashed, you add 8 zeros to the end of it. And in base 2, the same kind of rule applies. If I multiply a number by 2 to the k, well, in base 2, it's as if all of the digits shift over by k units. And so I add k zeros to the end. So when I multiply a number by 2 to the 8th, I just need to add 8 zeros in base 2 to this number. When I multiply this number in base 2 by 2 to the 4th, I add 4 zeros to it. And this number stays the same because I'm multiplying by 1. So that's nice and convenient. So I wind up with the orange number, the blue number plus 4 zeros on the end, and then the green number plus 8 zeros on the end. And I'm doing addition of those three things. And the nice thing about addition is, well, it doesn't matter what base I'm in. I can write the numbers in this way, and if I want to sum them, the addition is going to proceed in the same way. There's no point at which I have more than 1 1 in the same column. So all the orange digits are just going to drop down, all the blue digits are going to drop down, and the green digits are going to drop down. And I'm going to be left with the base 2 representation of this number, which is 1010, 0111, 1101. And you might say, well, that seems quite fancy, but at the end of the day, I'm only really doing one thing. I'm taking A, and I'm saying, what's the base 2 representation of it? It's 1010. I'm taking 7. What's the base 2 representation of it? It's 0111. And D is just 1101, and I'm taking those 3 blocks and joining them together. So the conversion between base 16 and base 2 is actually very straightforward. The only thing that you have to do is remember what A, 7, and D are, and then you just concatenate all their representation in base 2 together. So you don't even have to do any arithmetic. You just say, what's the base 2 representation of each of these 3 digits, and combine them together, and that winds up being your base 2 representation. The reason why this works so naturally is because 16 is a power of 2. So for that reason, it will always be very easy to convert a base 16 representation of a number into its base 2 representation. If I wanted to go in the opposite direction, it's really just as easy, because if you gave me this number, I would just divide it up into blocks of 4, and I would say, well, what's 1101? It's D. What's 0111? That's 4 plus 2 plus 1. That's 7. And what's 1010? That's 8 plus 2, which is 10. And so that's A. So if you gave me this number, I could very quickly divide it into blocks of 4 and reconstruct that it's A7D. For that reason, conversion of numbers from base 2 to hexadecimal or vice versa is actually very easy. And when we think about what hex really is, it's binary, but without having to store quite as many things. So you're using a quarter the length of the string, right? Working with a number like this would be tedious, but our brains are very comfortable working with more than just 2 digits. We work with 10 digits. So base 16 is close to 10. We just have a couple of extra, 6 extra symbols that we're using to represent this. But rather than looking at this number and trying to parse it in this way, we can just think of it as A7D. So everything that happens in the computer happens on the level of binary. Often how we think about, or how we, what's the right word? I can't think of the right verb, but how we're going to represent everything in a way that makes our human brains understand it a little bit easier. As you can see, my own human brain is a little bit limited. is going to be on the level of hex, which is just a simplified representation of base 2 with a quarter as many digits. We have seen this, so when we've worked with colors thus far in the course, we've seen hex numbers, hex strings before. So the first 2 digits in an RGB representation of a color correspond to the amount of red, the second 2 correspond to the amount of green, the final 2 correspond to the amount of blue, constituting that number. So if we look at a number like 00FF00, what that means is, well, we have 0 red and 0 blue. We have the maximum amount of green on the green channel. So the number FF, well, that's 15 times 16 plus 15, which winds up being 255. So all we know at this point of the course that the amount of red, green, and blue in the RGB representation of a color allows us to say each of these channels is an integer between 0 and 255, and now you're maybe starting to appreciate why that is, because FF is 255 in base 10. So we have 2 hex digits allocated to each of the colors, which means that the numbers are going to range between 0 and 255 inclusively. So we've seen it before. We've also been around this concept. So I want to show you an example of, in the sandbox, we could define our own class, and we worked with shapes when we introduced the concept in Python of user-defined classes. So we could have a circle, and maybe this has an init function associated with it. Just to initialize this, so this is before we move to data classes, and I'm just going to set the radius of the circle. I'm not even going to have a center of the circle. And then in main, what I want to do is say, let's have a circle that sets the radius equal to 5, and then I want to print C. And this is kind of our classic way of defining a class and then creating an instance of that class, and now we're going to print it. And we don't have a data class, so we don't have a printing kind of built in. And we've not defined an REPR function, so we don't have a natural way of representing this circle, at least not yet, as a string that we can pass in when we print it. If I leave that REPR function blank and then I run this, what I see gets printed is a circle object at something. And so we've touched on this very briefly at a point in the course before. But what this tells us is, it tells us that we have a circle object. It doesn't actually tell us anything about its attributes, so it doesn't print the fact that its radius is equal to 5. What it prints in this particular case is that it's a circle object at 0x7f08071a1150. And we can interpret this, what this is saying here is that the 0x set is essentially a shorthand to a human saying everything after this should be interpreted as a hexadecimal number. So 0x essentially just means read everything that follows as a hexadecimal number. And then everything after 0x is the hexadecimal number. And in this particular case, this is representing a memory address. So the memory address here that is getting allocated on the computer that's running this particular installation of Python is 7F08, etc. So this allows us to say in the RAM there is an address, an actual location, and the label, the address associated with this location is this number. So it's as if you go to a storage facility and all the storage facilities are not, the bays that are at the storage facility are numbered. It's the same idea here. You need to make sure that you organize your data well so that you label all of the possible locations you have access to. And this is the location for this particular circle object. Everything is going to get assigned to a location. It could be an integer or a string or a much fancier object. Regardless of what it is, everything eventually winds up getting stored at some location. Now, in this particular case, there's a natural exercise, I suppose, which is to say, when we look at this, how many addresses are there if, in this case, and here I have slightly different address because it was a different run, but we have 7F91DADD4810, and that's our memory address. And you can see that there's 12 digits in this memory address. So as a quick check, we might say, how many addresses are there in total if they're represented by these hex numbers containing 12 digits? Just let me know in the chat. Okay, there's two answers here. X is 16 to the 12. Okay, good answer. How did we get that? Well, maybe there's 16 options for each of the digits. They're all independent of each other. So if I want to know the total number of different ones, we can multiply all those possibilities together, and we get 16 multiplied by itself 12 times, so 16 to the 12th. The other answer is to then say, well, when I write that out, what is 16 to the 12th? And it's a pretty big number, right? It's also 2 to the 48th, which is another way of representing this. Or I could, if I really care about trying to place this in terms of numbers that I can kind of conceptualize, I might convert that into base 10. And the implication here is that this computer has a huge number of possible memory addresses. 16 to the 12th, or 2 to the 48th, is 250 trillion. It's a big number. And you might say, well, I know that my computer, most computers that we're going to work with are not actually going to have 250 trillion addresses, because if you know anything about how much RAM that you have, you might have 64 gigabytes of RAM or 128 gigabytes of RAM if you're watching this on a computer. But giga, the prefix there is billion, not trillion. So there's a note here for the mathematically curious, which is that the computer does not have, that we're running the sandbox on, does not have 250 terabytes of RAM. The address that we're working with is what's called a virtual address. So it is assigned a location that is a hypothetical location, and there is a real location associated with it, but it's not at this particular address. This is a virtual address that is presented to you so that you can understand where it's stored. I think there's complicated reasons for this, and getting into that's far beyond what it is that we want to do, but I did want to at least point that out. There's an opportunity, of course, to ask another question, which is, well, if we can do arithmetic in base 2 or we can do arithmetic in base 16, why is it that we use base 10 in the first place? Why not use base 8, base 11, or something like base 16? Meg says 10 figures. 10 figures of what? Like collectibles? There we go. I think maybe that was a mistype. Okay, Felipe says five fingers on each hand. Many of us do. All right. So that's the answer. There's nothing really special about base 10. And nevertheless, because we have 10 fingers and 10 toes, we've encoded our numbers. We've agreed that that's a particularly good base to encode our numbers in. And in fact, the word digit, which I've started using to mean one of the elements that combine to form numbers, right? So strings of these elements represent numbers. Well, one of the ways that you could define that is according to the base 10 representation of the number, but it's more general than that. That's what this is Merriam-Webster. 1B is implying that you don't have to be on base 10 for a digit to mean a digit, to mean one of these elements of or units that we combine to represent numbers. But the word digit also has other meanings in the English language, one of which is, well, our fingers and toes, and the other is that we even used, this is an older meaning, but we represent the width of fingers as a way of measuring things. And so all those combine into one single English word, but the idea I'm trying to present here is the idea of fingers and toes are inextricable in the English language from the ways in which we represent numbers. And I love this particular unit of measurement, especially because it does still have isolated uses throughout the world. I think, in certain parts of the world, you measure haircuts in number of fingers, for examples. But it's largely, I think, something that we've, when we use the word digit to mean one of the constituent numbers in a larger number, we're not thinking of that as being inherently connected to fingers and toes, but that's how we've chosen base 10. And everything works mathematically in any base that you might want to pick. So the multiplication algorithm, for example, that you've probably learned a long time ago, of taking each digit and multiplying it by each digit in the other number and placing the result with carry, and making sure that every time you move to the next digit, you add a 0 to the end of what you're multiplying together. It's not actually, if you thought about trying to explain that, I guess, as you might know if you happen to try and teach young children mathematics, but if you actually try to write down precisely how this algorithm works, it's not that easy to explain, but it's something that's kind of hard-coded into our universal basic education. So we're comfortable with it because we all have learned it, often by rote memorization, but precisely writing out how it works might be challenging. The point becomes, if we had learned all of math with respect to another base other than base 10, well, we would wind up with the same multiplication algorithm and it would still hold. So, the numbers that are going to look the most comfortable to you, when we look at this, the product of these numbers, you probably, in the same way that your eye maybe gravitated towards Python, I would imagine that your eye is going to gravitate towards this product, because here you're comfortable with saying 4 times 40 is 160. 4 times 40 is 160 again with a 0 on the end. And 1 times 40 is 40. With 2 zeros on the end, you add up all of those three things, you get 5,760. So I'll give you for free that this is base 10. And I'll give you a hint that this is going to be base 2. This is the representation of 40 in base 2, and this is what 144 looks like in base 2. So this is the same multiplication algorithm, 0 times 0 is 0, and so forth. Eventually we get a 1 times 101000, but we also have 4 zeros on the end, so that's where this comes from. And we continue in that way, and eventually we add up everything, and if we have to carry, we carry, but we wind up with a final product of this, which is the number 5,760. So we're still able to do basic arithmetic and the algorithms for it, regardless of the base. So there's nothing special about base 10 or base 2 or any of these other bases. Any thoughts on what the other two missing bases are? There's something so weird about seeing 4 times this number 5, and then seeing 316. It seems like it can't possibly be right, right? Good guess, Chris. You said octal. Okay. Octal is base 8. So we know that 4 times 5 is 20, I think, in base 10. And in base 8, 20 is, well, you have 2 times 8 is 16 plus 4. So that digit would be 4. So it can't be base 8 because then we would know that this would be a 4. It's almost like a puzzle. You can try different bases and you can see which one is wrong. Yeah, so good job to Remy. This actually is base 7. All right. And you don't get any bonus points, and it doesn't matter if you got that, but if you did, good job. And, the thing on the right actually could be a variety of different bases. I said it could be base 20, so it could be from the Maya. And the point being that there's nothing inherently special about base 10 at all, actually. And, don't tell that to the people who love SI metrics for measuring things, because I'm not one of those people myself, but I'm also not someone who's in the Dozenal Society of America, which is trying to get us all to move to base 12 for some unforeseeable reason. I think base 2 and base 16 are really nice because that's how we've set up computers. And so I think if we had everything to do over again, it might make sense for us to just use base 16 for all of our math, and then that would make computers easier to work with, but who knows? There are all these remnants, though, of non-base 10 stuff in how we think about things. So time, of course, is this weird combination of base 12 and base 60. And then there's historical examples of things like the Gettysburg Address. It's a great Pennsylvania reference. And Abraham Lincoln saying 77 years ago, where score means 20. So when he says 77, it means 87. Which coincidentally, in other languages, you see little remnants of this. So in French, you have 80, which is 80, which is 4 times 20. Anyway, that's enough about bases, but we have to have this appreciation of bases for what we're going to do, because when we get on the level of the machine, we better be comfortable with base 2. And we can be comfortable with base 16 as a proxy for base 2. But we need to understand how everything is representing ones and zeros on the level of arithmetic. Okay. Meg says imperial units are always weird. See, I disagree. I love imperial units, especially for stuff like volume. Because I never really, does anybody ever, truly use something like a deciliter? Has anybody ever unironically said, can you go and get me 3 deciliters of Coke? I don't think so. But the imperial units are all really nice because it's, everything is actually in base 2. You have 2 pints in a quart, 4 quarts in a gallon. Was it 2 cups in a pint? And a cup is 8 ounces. So everything is a power of 2, and it has this nice, beautiful set of relationships among it. I understand exactly how much each of those relationships are. And then you're going to say, well, everything, because of all the Swiss scientists or whatever, they standardized everything, right, across a lot of different measurements. So you have this wonderful fact that, a liter is a kilogram. A liter of water weighs a kilogram, which is cool, and that's very nice. But in imperial units, we have the exact same thing. A gallon of water weighs 8 pounds. And that wasn't always the case, but it was close, and then they re-standardized it. So it would be the case, which means a quart of water weighs 2 pounds, and a pint of water weighs 1 pound. So you might not like imperial measurement, but my sense is that it's always been very forward-looking into the realm of computers, and we need to go to all the SI people and say, actually, you chose the wrong base, and it was all because of this humanist over-worship of our fingers. A pint's a pound, the world around. I love that. What's the origin of that, Ben? All right. Okay, so we're going to use this to implement some assembly language. And you might think for a moment, like, what are the operations that are going to be helpful here? Right. In fact, tell me in the chat. Right. If we're going to have individual, like, built-in functions in our computer, where we've got a central processing unit, and then we've got a memory bank of a bunch of locations. What is it that we need to do when we're working with that? And in other words, we're going to have built-in building block functions that are going to be part of this architecture. What would be good ones to have? And if you have no thoughts, that's all right too, because I'm going to show you. Vivek says, call the function and execute them. That's good. We're going to be lower level than that. So the only thing we can really do is stuff like what Lori is saying. The absolute foundational things are, I have something in a register, I need to put it in the RAM somewhere at a particular location. Or I'm going to go in and read this particular place in the RAM, and I'm going to grab it and I'm going to store it internally, meaning I'm going to place it in one of my registers near me so that then I can manipulate it. And then when we say manipulate it, well, we might think about what are the very basic types of manipulations that we want to perform, and anything fancy that we might come up with probably should eventually boil down to some kind of arithmetic or logic. So we're going to have, and I'm going to show you, probably maybe our simplest instruction that we could have is something that adds two numbers. And in particular, if I'm reading stuff in from the RAM and I want to add the result, I'm going to grab, something from the RAM, and I'm going to store it in two registers, and then I want to add those registers together. So there will be an instruction, and I like thinking about this as, a function of some kind, but this is much more base level, as you're going to see, than a function, because it's going to perform something that's extremely simple. And in this particular case, it's just going to do an addition. So the function is not a function, it's just the addition of two registers. If I were to say I've got two registers, they could be register 4 and register 7, it doesn't matter what they are, and then I want to take the result of adding those two things and place them in another register, I'm going to call that register D, then I could also encode that instruction itself as a sequence of digits, and in particular a sequence of bits. Here the term bit is a portmanteau of the words binary and digit. So a bit is just a binary digit, meaning a 1 or a 0. And this particular instruction here says the first 4 bits are going to be the instruction, and the add instruction for the computer we're going to work with is going to have code 1. And what is 1 in hex? It's 000, or in binary it's 0001. So if the first 4 bits of this string of length 16 are equal to 1, or equal to 0001, then the instruction is going to be encoding an addition. If that's not the case, I see 1101. Well, those first 4 bits are going to represent a different instruction. But if I see 0001, how this computer is going to work, this Xtoy hypothetical computer that is a little bit of a simplification of real assembly language, but I think a very teachable one and transferable one. It's always going to say 0001 means add. So inside of the machine is forced to make a deterministic execution of something. And that execution is to say, well, I'm going to store into register D, meaning whatever the next 4 bits in the instruction are. And for this particular case, we have 0010. What is that? Is the number 2. So this says add into register 2 the result of whatever the next 4 bits are. That's going to tell me which register I'm interested in. And then the final 4 bits are going to tell me what the other register is. So 0010 is 2. 1000 is 8, because you have 8 plus 0 plus 0 plus 0. And so the idea of saying set register 2 equal to register 2 plus register 8. So this is like saying register 2 plus equal register 8, because you're adding to the existing value whatever you see in register 8. I'm not adding 8 to it. I'm able to say, look at register 8, which could have a large or a small value. I don't know what's there, but take what's in register 2, take what's stored in register 8, add them together, and place the result in register 2. That might not seem like much, but the whole idea here is that I've taken the idea of doing something inside of the computer, performing an addition, and I've represented that concept with 16 bits. Okay, so if I told you this was how the computer worked, and then I gave you these 16 bits, well, you'd be able to determine the first 4 bits are, correspond to the number 1, which is an addition. These next 4 correspond to the number 2, so I'm going to be entering the result into register 2. And then the next 4 correspond to a 2, so I'm adding register 2 plus whatever this is, which is 8. So register 2 plus register 8. So I could hide all of this, and you'd be able to tell me what it does. But the point is, I get a 16-bit or 16 binary digit string that represents doing something in the computer. This is a very powerful concept, because it means that the computer is not just going to have storage that's represented as binary numbers. It's also going to have instructions or things that it is executing stored as strings of binary numbers. So this is the first hint of what I'm talking about with the dark art of computer science, that you have these 2 seemingly different ideas, that you have storage using binary numbers, but now we're also going to have functions or execution represented as strings of binary numbers. And where you have binary, you also have hex. So would we as humans think about this as a 16-bit number? That's ugly. Instead, I'm going to use my conversion that we had previously, and I'm going to say, well, this 0001 is the number 1, 0010 is the number 2, same thing here, and then 1000 is the number 8. Of course, if I saw 1010, for example, well, then I would need to say, well, that would be 10, so that would be an A here, right? So the idea is I take sets of 4 bits at a time and convert each collection of 4 bits into its hex representation for that number. Pretty cool. If I can do an addition, I can do a subtraction. So how we're going to program the computer, or think about the abstraction of the computer, is that if you see 0010, and that's the number 2, if those are your first 4 bits, well, then everything that follows is going to be a subtraction. But what's nice about Xtoy is that the syntax, so to speak, is going to be the same. So if I see a subtraction in the first 4 bits, meaning 0010, Well, I'm still going to enter the result into register D, whatever these next 4 bits are. But instead of doing register S plus register T, I'm going to do register S minus register T. So this is 2 and this is 8. And so the first 4 bits correspond to 2, the next 4 correspond to 2, 2, and this is 8. And so as a hex number, this string of 16 bits is 2228 in base 16. It's the same format as the addition, but the instruction at the start of this is not a 1, it's a 2. And so as a result, it means a different thing that we're going to execute. So we wind up with a different instruction. However, at the end of the day, it's an instruction that takes up 4 hex digits, which is nice because if I just gave you 2228, you'd say, oh, okay, well, it's a subtraction. I'm setting register 2 equal to register 2 minus register 8. And so again, the computer is doing something, but that task can be represented by a pretty short number. And we can continue. So if we have an addition and subtraction, we also need to do stuff like, read in something from memory, write to something from memory. We're going to have a special, one of our instructions is going to be 4 plus 2 plus 1, which is 7. So if the first 4 bits correspond to 7 or 0, 1, 1, 1, the next 4 bits are going to be the register I'm setting it to equal to, and then the final 8 bits are going to be the value that I'm setting register D equal to. So this is in the same way that we're kind of reinventing the start of programming. When we're doing addition, this is like saying x equals y plus z, but now we're representing it as strings of 1s and 0s. And this is like x equals y minus z, where we are able to do a subtraction. And now this next one is like saying x equal to 47, right? So if the instruction code is 7, then we're going to be able to set this particular register. 4 plus 2 is 6. So register 6 gets set to whatever this value is. And that value is, in base 10, it's 200. I think this is the last time in the slides you're ever going to see me represent a number in base 10 because, as I've said, base 10 is a very selfish base that doesn't really connect to anything in a computer. And so we're going to ignore it. Rather, I'm going to think of this number not as 200, but as C8. And why can I convert that to this number to C8 in base 16 very quickly? The reason why is because, well, I know this is 8 plus 4, which is C. So 1100 is always going to represent C. 10000 in base 16 is 8. So we have an instruction here that, again, is a 4-digit hex instruction that is 76C8. And if I saw that instruction, I would say, great, I'm going to set register 6 in the computer equal to C8, which again, we think of as 200, but in base 16 is just C8. I'm about to show you all of this in the program itself, but I need to give you like a couple more instructions so that we see enough that we can work with. The fourth instruction is load. And in load, it's very similar to load immediate. The instruction code is 1000, so that's 8. This says not set register D equal to a particular value, but look at the memory address corresponding to these 8 bits. Go in and copy whatever is there into register D. So this is 8. The instruction is 8. If the first 4 bits are 1000, we're always going to be loading. The next 4 bits are always going to be what we're loading into. So if 0100, that's 4. And then RAM address in this particular case is 8 and then another 8. So we're setting register 4 equal to whatever we see at memory address 88. We're not setting it equal to 88. We're going into that address and set it equal to 88. Note, I'm not saying 88 because everything here is in base 16. And as a hex number, if I wanted to do this, I would say 8488. Okay, that says load into register 4, whatever is at memory address 88. And for our fifth instruction, this is going to go in the opposite direction. So if I have something in a register and I want to push it out to the RAM, well, the instruction here is going to be 1001, which is 9. The next 4 bits are going to correspond to the register that I want to move into the RAM. And then the final 8 bits are going to correspond to the memory address in the RAM where I want to put this. So again, this is 88 again. This is 6 again. The only thing that's, or this is 4 again, excuse me. The only thing that's changed between here and here, between here and here, is you're going to notice I changed 1 bit. But that 1 bit changes the direction in which this is happening. So in the case of load, I'm reading in from memory address 88 and putting it into register 4. In the case of store, I'm going in the other direction. So I'm taking whatever's in register 4 and I'm pushing it to address 88. As a hex number, that's 9488. We have 5 of these operations: addition, subtraction, load immediate, load, and store. These two are very similar because we're setting register D equal to an arithmetic operation involving registers S and T, whether that's the addition or the subtraction. For load immediate, I'm saying set register D equal to some value. For load, I'm saying go into the memory address that's given and set register D equal to whatever is at that address. And then for store, we're pushing in the other direction. So I'm saying take whatever's in my current register at D and push it into this memory address, copy it over. It means that we can also have an example program and an opportunity for you to think about this. So what might this program do? I'll have you remember that 7 is load immediate. So set the register that's indicated equal to some value. And 9 is store. So 9 says take what's at some particular register and push it into a given memory address. And 1 again was an addition. So tell me what you think. What is it that this program does on the level of each of the 4 instructions that constitute it? Or maybe I stumped people. So let's take a look. We're going to break this down one instruction at a time. We have 7 1 C8. So 7 is a load immediate. So it says register 1 is equal to C8. Register 2 is equal to 1E. And then we want to add these. So register 2 is equal to registers 1 plus register 2. And then we want to take whatever is in register 2, we're going to store it at memory address 46. So once we have done that, well, R1 is equal to C8, R2 is equal to 1E. R2 is now equal to, and here's where if you had used base 16 your entire life, you'd say, of course, obviously, C8 plus 1E is E6 because I'm good at math. And then we're going to take that value and I'm going to push it into memory address 46. Again, note, I'm not saying 46 because everything here is going to be represented in base 16. And this is a simple program, but, you know, it's kind of similar to a program that says R1 equals 200. Again, I'm doing I lied. I said that you'd seen the last form of a base 10 number, but you haven't. C8 is 200. 1E is 30. And you see my point, like, you'd say, of course, 200 plus 30 is 230 because we're comfortable with base 10. But the idea is register 2 is R1 plus R2, and then some other variable is equal to R2. Now, obviously, everything is going to happen behind the scenes for you. Python or whatever programming language is going to manage the registers and the memory locations, and that's going to work with the internal symphony of your computer and make sure all this is handled and that it's working very quickly. You may get a variable in a register at some point in time or in memory or both. You don't have any insight into this, how exactly the symphony is going to work, and that is a good thing. And this is, I think, we're hinting at what ultimately we've obtained with Python is an immense abstraction. So at the level of ones and zeros, programming a computer is a real pain in the neck, as anybody who has worked with like punch card programming could tell you, that, you know, and the higher the level of abstractions that we have, you know, developed as a society, we've gone away from the electrical side of the computer, but we've empowered ourselves. And from that perspective, AI represents the next step in that direction of abstraction. We no longer necessarily constantly need to type every single character in a programming language on our own, because we have the next layer of abstraction for doing something, which also is immensely empowering because it means we can do more faster. And so we're delving into the other direction so that we don't lose sight of how everything is working. It's critically important. It's never been more important than it is today because electrical engineering is very important with the design of chips. But the whole point here is that the program itself is really just a string. Another way of saying this is it's a sequence of integers. It's like a tuple or a list of integers. And each one of those integers encodes one instruction. So it tells the computer to do something very simple, but it's able to tell the computer to do something. And if that's the case, then what a program becomes is a sequence of those instructions that hopefully combine into something more complex. We're going to look then at Xtoy. So let's take a look. And with Xtoy, it's going to tell us you need to encode each line of the program in the memory. So remember, the memory is going to store things like variables and so forth. But again, step one on our journey into the dark heart of computer science is this concept that the memory will have variables in it and numbers, but it's also going to have instructions in it. And so I'm going to show you the same instructions that we had before. The program is always going to start at line 10, not 10, but 10. So if I type 10 and then colon in this simulated assembly language program, then this is going to allow me to indicate precisely what is contained at memory address 10. And what's going to be contained at memory address 10 is the instruction to load into register 1 the value C8. And I can do that with 7, 1, C8. And when I type that, something happened in the program, which is that it automatically color-coded the instruction in this color of blue. And then this here is an automatically generated comment. And the comment is just saying what this instruction does, which is to set register 1. Notice that it uses this little left arrow to say we're setting into register 1 the value 00C8. And I'm going to add the remaining lines one at a time, but I'm entering these into subsequent memory addresses of the computer. So at memory address not 1111, I'm going to set register 2 equal to 1E. And we think of that as the number 30. But in hex, it's 1E. And then at line 1, 2 of the memory, I want to add registers 1 and 2 together and place the result into register 2. So the next hex digit is where this sum is going. And then the final 2 digits represent the registers that I'm adding together. So even though it's a 4-digit hex string, when I type it in, it automatically gets this comment, register 2 equal to registers 1 plus register 2. Finally, I'm going to, in line 1, 3, I'm going to store register 2 into memory address 4, 6. So 9 means store. Register 2 is going to be the register I'm storing, and I'm placing it into memory address 4, 6. So now you see the comment says set memory address 4, 6 equal to register 2. All right, and now there's a key point here, which is I also need to end the program. So when the program starts, there is a special register. I want you to think about a special register called PC, or the program counter, that always starts at memory address 10. And as it executes lines, unless we tell it differently, now this is going to get you thinking hopefully about the other types of instructions we're going to have. And there's very much a spoiler alert over here on the right because it's telling you what all of the different instruction codes represent. That's cool. But in the meantime, if I don't tell it to do anything differently, it's always going to start at line 10 or memory address 10, and then it's going to just jump one at a time. So it's going to go 10, 11, 12, 13. We need to tell it to stop, and we don't actually have to because it's going to be the default. All addresses in Xtoy are going to start off as equal to 0000. And it's nice because 0 anything, so I could do 0 FAB, 0 fab. That's going to mean halt. Okay, and that's because 0 followed by any 3 hex digits, I can put anything I want there, and it's always just going to be halt. So that tells the program counter to stop proceeding, and the program is going to exit. We can also take a look at this. So we can visualize this. We can go into this simulation mode. And this is nice because it shows me kind of a like an old school hypothetical display here. But I want you to see for now, we're going to look at standard in and standard out and all that stuff later. But I want you to notice in this particular case, and we can expand this, I think, to see more. Yeah, oh no, that just zoomed it. We can scroll back and forth and see the memory addresses. Note, all the memory addresses start off as equal to 0. Okay. So it is a convention that the program starts at memory address 10. I'm not really sure why that is. It could have started at 00. I think it's giving you these like extra addresses here in case this is temporary variable storage. I'm not really sure. But you do just remember that we always start at memory address 10, and I can run the whole thing, but I could also step it one at a time. So when I click step, it's going to advance the program counter 1, which means it's going to go down to line 1, 1. And so this is in the memory, we see 71C8. And so it follows the instruction to load into register 1 the value C8. And you'll see that here. So here are all the registers represented. And again, all of this, of course, is virtual, but very, I think, helpful in terms of understanding what's going on. Register 1 now is set to C8. The next line is to set register 2 equal to 1E, so you're going to see that updated when I step it. line 1, 2 says 1, 2, 1, 2. So add these two registers together and store the result in register 2. So you're going to see this 1E get updated to the sum of the two, which is equal to E6. And then finally, line 1, 3 says store register 2 into memory address 46. So we're going to push that into memory address 46. You look there, it's currently 0. When I step it, that line has been executed, and I'm going to see line memory address 46 get populated with E6. And that's our program. So that's our kind of our first XTOY program, and it has stopped because the program counter hit line 1, 4. If I reset this and I run it, it's going to execute all these steps with a slight delay, and then we're going to stop when we get to line 1, 4. So the program doesn't do a whole heck of a lot here. It just reads in two values, adds them, and then writes them to a place in the memory. So let me show kind of one extra wrinkle here, which is that we also could write to a particular location. As I said, sometimes when you write to a particular location in the memory, in the RAM, it causes a disk operation or something to happen to the display. There is a special reserved memory address called FF, and that represents standard in and standard out. So I want you to think in terms of standard out. We're going to think about this as printing. So if instead of storing register 2 into memory address 46, if instead I stored it into memory address FF, you're going to notice this changes to write register 2. So it's when you see write, I want you to think about this as printing register 2. So you're going to see it appear here in standard out. When I reset this and I step, so I load in C8 into register 1, step, loading into register 2, adding them together, and then finally when I execute this instruction 92FF, you're going to see E6 appear here because that's what's in register 2. It also appears at memory address FF, which can be overwritten, but you'll see that appear in standard out. Okay, so this is the other place that standard out is representing data. So we can think of this as like printing to the console. I also can load from this memory location. And if I were to load from memory address FF, I might do this instead of just loading immediate. So let's do 7, 1. Instead of 7, let's do 8. And let's do 8 here. So that's going to load from a memory address, but I don't want to load from C8. I want to load from FF. So that means like read in a value from the user. And 821E, instead of that, I'm going to do 82FF. So I'm going to read in a value from the user and place it into register 2. Still going to do the same thing. I'm going to add those two values together. I'm going to write them to the console, and then I'm going to halt. But now in standard in, I should probably give these standard in some numbers. So we could add the same two numbers, or we could get adventurous and add 3 and 5. Okay, it doesn't matter what we have. And now when I run this again, you see standard in is here. I can also click here, and this is going to be where the memory is represented. When I step now, I read in to register 1 from standard in. So you see 3 has been read in. And this is something we're actually familiar with. So how standard in is getting represented here is as a queue. I put in 3 first and then 5. So 3 is going to come out first, just like with a queue, and 5 is going to come out second. If I look at the memory, I'm at line 1, 1, so I'm reading in from standard in again. So it's like I'm grabbing the number 5 from a user. I'm reading it in, placing it in register 2. I don't have anything else in standard in. When I step again, I add the two things together and place them in register 2. So this is going to get updated to 8. And then I write that value to the console. So I've taken in 2 integers from the user, I've added them together, and then I've printed the result of that addition to the console. So FF represents kind of both of these things. It can allow me to read something in, and it can allow me to print something. which for the purposes of what we're going to do is going to be plenty. Think of it almost as like, the command line arguments that when we've written a program previously in the course, we have command line arguments that we pass in when we run that function. And this is a way of like reading something in from that. There's just one more note I want to make though, which is if I can remove both of these. Say, for example, that the first number I want to pass into this program is FFFF. And the second number I'm going to pass in is 0002. You might wonder what happens when I run the program now. So if we were going to add the numbers FFFF and 0002, we could follow the standard addition algorithm and say 2 plus f. Now in base 10, we know that that's 17. But in base 16, 2 plus f would be a 1 and carry the 1. And 1 plus f would be 0 and carry the 1. And 1 plus f would be 0 and carry the 1. And 1 plus f would be 0 and carry the 1. We wind up with the number 10001. What happens when I run the program is I read in FFFF, I read in 0002, but when I add them together and place the result in register 2, I don't have enough space. So that 1 that was at the start of that number gets truncated, it gets thrown out. And when I print the number, I don't print 10001, I just print the number 1. This is a great example of integer overflow or overflow in general. And if we've worked with Python, it's not something that we've been inherently familiar with, but if you program in a lot of other languages, it's something that is really, constantly on your mind as a possibility that we have an amount of storage associated with any variable. In this case, it's an integer. And what I want to stress here is the amount of storage that you have in Xtoy is just 4 hex digits. So the fancy way of saying this is that arithmetic in Xtoy is done modulo 16 to the 4th or 2 to the 16th. And what that means is we're simply taking the remainder after we divide by 16 to the 4th. So in base 16, the number 10001, when you divide it by 16 to the 4th, you get a remainder of 1 because it's 1 with a remainder of 1. That might be a little beyond how I want you to think about it, but I think it's useful. And the purpose of this particular example is just to show you that storage is finite. And when you add 1 or 2 extra numbers beyond the largest number we can store, which is FFFF, everything's just going to wrap around. So there's this like cyclical nature to the arithmetic that you're going to do. We have a lot more to do. Remy, you have a question of why 46? Why did I do memory address 46? Sorry if I didn't answer that question. There's nothing special about it at all. I just picked a number. So you can put it somewhere else if you like. Doesn't matter. But I was just showing you that it does show up elsewhere. The most important thing and why I show that example before we do the printing, the most important thing to realize here is that the memory, again, I'm saying this one more time, but it's our first step on the journey to the dark heart, is that the memory contains 2 separate things. It contains the program, and it also could contain like other stuff. So we could also have like variables and things like that that are stored in the memory. And that might not seem like much, right? That the memory is representing these 2 things. Actually, it has a lot of implications. So we're going to see that at a later time. In the meantime, what we really want to do is, appreciate how this works, but we have 16 total operations. We've only seen 5 of them. So next time I'm going to cover all of the remaining operations. And what we're going to see is a lot of these operations are pretty straightforward. There's nothing that's doing anything that much more complicated than an addition or writing to memory or reading in from the memory. They're going to do all this stuff with basic arithmetic, but also allow us to jump the program counter to different places. But what we're going to see is even though those operations are pretty rudimentary in that they can be represented by 16-bit or 4-hex-digit operation codes. So just the program itself is just a bunch of strings of numbers. That makes it seem like the program can't possibly do very much useful or interesting. And that could not be farther from the truth, because at the end of the day, every time you run a program, it is, according to this very complicated symphony of abstractions, eventually getting, converted into a collection of machine instructions that can be represented as ones and zeros to tell the machine what to do in every cycle of the computer. So that's what I want to show you, is the ability for us to come back to a program that is a real program of something that we have already seen in the course that does something that I think is pretty sophisticated, and actually implement it on the level of hex instructions. If we can do that, we're going to have, first off, an appreciation for people who have made programming languages so that we can do more complicated things faster. Hopefully, I think you'll understand what AI truly is from the perspective of programming, which is the ability to jump a level of abstraction, and who knows where it's going to go and what the level beyond that might be one day. But it's also going to give us this appreciation for, in the other direction, how powerful computers are to do sophisticated things, even with very, very simple representations. But all of that is the subject of what we're going to have to do next time. So I hope you'll join me then. I look forward to it. And until then.